Hi guys, so welcome to this third session on Introduction to ABAQUS FEA software, which is designed for beginners. And in today's session, we will learn about performing static analysis using ABAQUS. The learning outcomes of this session would be, or from today's session, would be add addition to knowledge and understanding you have gained in the previous session. And you will also learn to perform and post-process static analysis motivated from a real-life case. And during this process, I will touch base on assumptions you can make to improve accuracy, and also how can you reduce the computational time if it is necessary to do so for bigger models. So some tips and tricks will be there. Okay, so as discussed in the previous session, general steps to perform any finite element based analysis includes pre-processing, post-processing, solution, and post-processing. So you already are familiar with that. If you are not, then please have a look at my previous session. But without wasting any time or in explaining these concepts, let's jump into the real problem which we need to simulate using FEA. So this is the typical one problem which I have brought in today. So we are supposed to perform in a static analysis using ABAQUS. So in this case, we have a thick steel bracket, as you see in the diagram here. And since we need to check its integrity, so we need to ensure that maximum principal stresses or von Mises stresses, it depends what criteria you really like. In this case, I would say let's go with the principal stresses does not exceed the failure stress. And in the context of integrity, when we talk about failure stress, so it's not the strength at which the material really fails, like ultimate strength or something like that, but it is the yield strength at which you will have permanent deformation in the structure and your structure's integrity will be compromised due to the permanent deformation. So in reality, if you look at different design codes, you will have this failure stress as the yield stress times some factor of safety, and that will give you that value. So what we are asked in this case is to assume the material to be isotropic as shown as written here, and we are provided the elastic properties of the material which is very similar to that of the steel. So Young's modulus and Poisson's ratio are given to us as material parameters, and we are clearly mentioned that we need to compare the principal stresses with the failure stress. As I told you, you can use some other stress measures as well, and again you can look at any stress analysis based textbook to understand what these are. And again, design code to design code, these requirements may change as well. So we are already asked to do so, so we're going to look into that. However, as I told you, in many cases you may be asked to compare von Mises stresses as well, and again you can look into my FEM related courses which I have already uploaded on YouTube, and also the quizzes where I have briefly discussed these concepts and try to give you an idea about when to use which type of a stress measure. So I will mostly be comparing it with von Mises stresses as well as principal stresses in this case. So as you can see here, our bracket has fixed face on this side, which is this face, while on the other surface here we have a pressure of 1 megapascals, and we need to find out at what load my structure will fail if the failure stress is 1 gigapascal. So again, we are given the strength value times the factor of safety here, so we really don't need to compute that on our own in this case. So moving on, if you look here, I have we are given the geometry of the steel bracket with the dimensions, and let's start setting up our model. So what I have done in this case, I have created the model here in a separate video, and I have brought it here with my slides. So what you see here is the sketch of the cross section, and so you may have to make this cross section sketch, and then you have to extrude in this direction and get the 3D structure out of it. Another important thing, in many cases you might not need a 3D analysis. Again, go back to my lectures and quizzes where I have discussed those concepts on plane strain and plane stress. So to reduce the computational time and to to make right assumptions, we have a symmetry in the loading along the thickness direction, and also we can assume, or we can see that the strains in the thickness direction due to this loading will be approximately 0. So for thick structures we can assume plane strain case as well. Again, when we say plane strain, some people use loosely the term 2D, but in reality it's not 2D, but in many textbooks you will hear about term 2.5D sort of thing situation, where you have only one stress component, strain component, which is 0 for plane strain cases, while you have other strain components and stress components due to the coupling of the matrices. Again, going back to that theory which I was mentioning before. Anyways, let's jump into the real software stuff now. So you can directly start with the 3D modeling, and as I told you, and based on the symmetry you can assume something. In this case, what I'm going to do is I'm going to start with a 3D to give you a feel of setting up a model, 3D model in ABAQUS, and then again, to construct this model in 3D, there are many different ways. As I give you one way, you can basically create this profile sketch and then you can extrude. But again, even to create this profile, there could be different techniques, because you have a lot of fillets here, as you see, R5s, and then you have some thicknesses and radii and etc. So if you're not familiar with ABAQUS, or you don't like ABAQUS pre-processing, you can use any other CAD software like SolidWorks, CATIA, Autodesk Inventor, for example. You can make your model there and you can then export it as SAT or a step file or an IGS file, and then you can directly import in ABAQUS as well. So it's not necessary to make everything here, but in this case I'm going to show you how you can make it in ABAQUS. So you can see, I will just go through it. You will start with the part as I explained to you. You can do with 2D, but in this case we're going to go with 3D and extrusion. What I have done in this case is I'm going to create a center line for this whole section, and then I will offset the lines, and then I will trim and then create fillets so that I will have a sketch out of it. So that's what I'm going to do here. So I'm still thinking, you see, there's a thought process behind it as well. Again, could be many different ways. Another way could be I can find these coordinates based on these dimensions, and then I can just draw lines and then use trimming and then also filleting to create these kind of fillets around here. So I'm drawing the center lines right now. So this line, then this line, and then maybe this line. So I'm trying to work out the coordinates based on the dimensions given to me. Again, when my mouse is not working, this means I'm trying to calculate this. Meanwhile, I'm doing that. when I started using ABAQUS back in 2000, 99, 2000 year, at that time ABAQUS didn't have any pre and post processors, so we used to have only the solver from ABAQUS, and that's basically when I was working in the industry. So in that case, we used to use different types of preprocessor. Like for example, in that case, there was a software called Ideas. I don't know if it's still available or not, but we used to use Ideas as preprocessor to generate the geometry, all the input boundary conditions, meshing, and then we take it to our finite element solver, which was ABAQUS solver. And then once its solution is done, then we used to generate a result file, and then we were then post-processing the data again in Ideas software. So it was not that easy, but now you guys are lucky that we have ABAQUS CAE, which can pre-process, solve, and do post-processing for us in a one-stop shop sort of solution. So here, as you can see, I'm trying to create offsets now based on the thicknesses. So on this side, I have, again, you have to go and look at the other drawing views as well in the previous slide. But you can see I'm just trying to create those right now. And so once the sketch is complete, then I will just create the fillets as per at the corners, as per the geometry on the right hand side. And also I have multiple lines, so you will see that I might be struggling with the filleting. So again, pay attention to that, how I'm dealing with those kind of problems as well. So in this case, you can see I'm just creating the offsets, but then there are a lot of lines which are crossing each other, and I need to have a close outer boundary of the sketch rather than all these lines. So you will see after a certain amount of time, when all the lines are connected, I will then start to remove those lines by trimming option. So here what I have done, I have now created everything, and now I start to trim the lines which are excess lines for me. Sometimes I come across problem that because I have small pieces of lines or small lengths of lines, so I need to zoom in, zoom out, and then also remove the right line rather than something else. So you see, again, you see here is a joint I have created, but then when I will be filleting this area, I will be struggling because fillet might be going from here to here, and it has 2 or 3 different lines or entities here. So I might have to modify that, but we will see how it goes once as we move on. So now I'm trying to remove all the excess lines so that I only have the outer profile of the sketch, which is on the right hand side. And yep, so again, if you're familiar with any other CAD software like SolidWorks or any other software, and you are more comfortable with that, then maybe use that to create the 3D part and bring it here. But it's easier to do it here and then do everything here rather than moving or shuffling around different softwares. So I prefer now to work in ABAQUS, but sometimes I have complicated geometries and I can't really work on that, so then I need to make it somewhere else and bring my geometry here as part or even as assembly. So almost there, you see my sketch is almost there. I'm trying to remove the lines which are excess in the middle, and I'm struggling with this line now because there is no intersect, so I cannot trim it. So I'm trying to create a line so that I can trim it then, and see, it worked. So now I have the section, and now I will start to do filleting using fillet options here. This is a create fillet option, and I already know the size, so let's start. I will have to select the fillet radius here, and then I have to select first line and the second line. So it's like clicking the first line and then the second line, and abracadabra. See, it's all done. Here I will struggle, I think so, and see, I am struggling here, and this one is working fine. First entity, second entity, keep an eye on these areas because ABAQUS messages normally appear here, whatever it is asking you to do. This line, I think it's better to create a longer line or select the outer line so that I can create a fillet. So that's what I'm going to do now. I'm going to remove, I think, the whole thing. I'm trying to find that segment which is intersecting, because the previous bigger lines were not intersecting, and now I can trim. So I somehow find my way, but in reality, if I had two continuous line intersecting, then it was just selecting the radius and selecting the two lines. So now I have done everything. I press done, and once I have pressed done, it will ask me for the thickness, which is the length, out of plane thickness of the beam or bracket in this case. So I just give that value and I press OK, and abracadabra, I have the geometry of my model, or the model for my thing. Now I will move to the property module and define material properties, which are Young's modulus and Poisson's ratio. So there are a whole range of material properties available, but in this case we have a linear elastic problem, so we're going to rely on that. So you just go to the material manager, create material. We are doing static analysis, so we're going to only define, in this case, elastic properties. Again, you can see there are lots of models. Again, this could be another course, so maybe I will come back with another course on how to do different types of material modeling in ABAQUS. So again, since I'm making everything in millimeters, so I have to make sure my units are consistent. So again, my Young's modulus is in megapascals, and Poisson's ratio have no unit, so it remains the same. Next, I create a section, because you can have one part with many different materials or many different parts or sections in one part. So I have to create section and assign to each section a specific material. I can create 10 materials there. So I create one section here because I have one part here, and I select only one material because there is only one material. And then I will assign this to my part, because as I told you, my part can have different sections and can have different properties. But in this case, it's easy. It's only one component or one part with one material property. When I do that, you will see it will give me the option. There is only one section now, just solid, homogeneous, and material 1. And when I change this, the color will change. This means material properties have been assigned. So once I have done that, now I go to the assembly module, and as any other CAD software, I will instance all the parts in the assembly module and assemble them together using different operations. In this case, it's only one part, so I will just go to next to step module and define a static step. So what I will do, I will press create step button. Then I will select the static step, because I can do many analysis like couple temperature, displacement, thermoelectrical, dynamic implicit, explicit analysis, static analysis, soil analysis. Somebody asked about soil analysis, so you can do that here as well. I'm not an expert in that, but you can do that. And static generally is the case in this case. So because everything is fixed, there is no rigid body motion. I normally prefer to have analgeom on, because if I can have large deformations, so my solver will not struggle, because it will use this non-linear geometric algorithm for solving. My input and output, as you can see here. So as you can see here, I have the total time for simulation as 1 second. Yeah. So is 1 second. So total, I have increased the maximum number of increments to 10,000, and I can have the time increment size from 0.1 to 1, because total time is 1. I have used it 0.1. This means I will get an output, or solver will solve in the increments of 0.1, 0.2, 0.3 as the maximum. Minimum can be up to 1 exponent minus 6, depending on the convergence of the solver. And this will give me a liberty that if I need output at different intervals, so I can get that as well. So that's why I have selected that here. Now I have defined my step. I don't want to do anything with the outputs. I'm using the default, but you can change the output, whichever what is required, how frequent they should be through this. So I'm just using the default right now. So if you click on these links, you should be able to see what outputs will be there and after how much time it will write during the solution. So next you go, oops, something went wrong. Yeah, we have been there. Yeah, so we have already been there. So there is no interaction, so I'm going to directly go to the load module now, and in this case I have to fix from the other side. So I can use this boundary condition button here and create a boundary condition, and I can also apply a load, which is a pressure on the top. So I am just rotating it using this rotate option. You can pan, rotate, zoom, etc. And now I'm going to apply displacement boundary condition here, and in this case I will select, I can name it, and I can select displacements here, press continue. It's a mechanical boundary condition, select the surface, and then I can fix in u1, u2, and u3. 1, 2, and 3 are the x, y, and z directions. Once I have done that, I need to apply pressure here. So now I'm going to go to the load button, and I will say select pressure, and then I will click on the surface, because it's asking me to select a surface for that. And then I can specify a value. In this case, it's 1 megapascals. Again, units are your responsibility as a user, so make sure that your units are consistent. Okay, so now my model is almost there. All the loading and boundary condition is applied. Now I can do some meshing. Again, for meshing, you have to do part by part. So always select the individual part and then start doing the mesh. So I'm selecting a global seed, which is the size of the element throughout the model or component. So you can see it looks something like this. And then I press yes, and you can see my mesh is very coarse. If I'm using reduced integration, again going back to my lectures or one of the videos, I can have zero energy mode. So at least I need more elements in thickness direction if I'm using reduced integration elements to remove hourglassing or zero energy modes. So that's what I'm doing now. I'm selecting it to define the edge seeds, and when I select the edge here and I do this, then I have more elements here, but still on the other edges I still have one element, so I need to do it for the other edges as well. And that's what I'm doing. So again, you have to play around with these things and see how they work, and it depends on the model as well. Sometimes you need to partition as well for meshing. Again, meshing is a very different area and it can be a full course as well. So again, my mesh, I am not satisfied because still I have many areas where I have single element, and then these are also very distorted elements. We need to have something more, so I keep on trying changing these densities and global meshes and see how it looks. Also, what you can do is you can, if you're not happy with that, then you can go to this mesh option, mesh controls, and you can apply with different options like bottom up approach, or you can do medial axis, or you can minimize the transitions. You can also have hex dominated. This means you can have combination of hex hex and tet mesh, excuse me. So that's what I have done here, and now I change the option and you see it looks much better than previous one. I have 3 elements, at least 3 or 4 elements in the center along the thickness as well. So and now I will check for the mesh quality and verify that it's okay. So there are no errors there, and what you see here is, if you look at the bottom of your screen here, you see there are no 0 errors and 0 analysis warnings. And now I will see if the geometric sizes are in limits or not, and again things look very good here. So again, if there is something wrong, you can go back and change these parameters which I just changed myself and see which one suits you the best. Again, this will not be the final mesh. You might have to do mesh convergence studies as well, as many design courses tell you. So based on that, you can see which one is giving you, which mesh will give you the best result. But obviously then you have to also see what is the consequences of that mesh on computational time. So you need to find kind of a compromise between the two. So in this case, I changed everything and now everything is set. So I will just go to the job and I will create a job and I will run it. So I will press create button, name a job, let's say test 1 or something. In this case, I'm calling it beam 1. Continue. I just leave everything default and I submit. I can write an input file and I can run it on command prompt. I can also do a data check, but in this case, I am gonna do a direct submit from CAE. As I told you previously, I normally prefer to write an input file and run through command prompt because sometimes CAE crashes and then everything gets really messy, you know. So, but in this case, it's a small model, so we can live with this. And many people do that for big models as well. It's not like ABAQUS CAE is not that bad. Just saying. Okay, so now I have run the simulation. You see there are no error messages. Output has been written after every 0.5 second. Message file will give you all the messages during conversion, and the status file tells you what is the status of the job. And then you press the results button and you will see the results. And you can see here your S measles stress is around 42 or something, if I can see correctly. So this is, which is much lower than 1 gigapascal. So I will go back and I will increase the load because I need to find out at what load the structure will fail. Okay, so now I'm going to increase the load, let's say to 5. Okay, and now I go back and rerun it. So you don't need to do anything more, just change the value, come back and submit. That's it. You can also copy this model as a different one and then you can run it separately, so you will have 2 different files for 2 different models. Okay, the results still running, so it's not finding ODB file, which is output database. Now I press the monitor button and you can see it's monitoring. There are no warnings or error messages, so now I go to the results. When I press this, now my stress should be higher, and you can see now it's 213 megapascals. So still 1/4 of 1 gigapascal of failure stress. So you can play around with different variables here. So here I'm trying to plot the displacement to see everything is consistent with the boundary conditions, and which looks okay to me. Stresses wise, this is measles. They ask you for maximum principal stress, so you can plot that as well, and you can see the values. Again, in this case, there's a slight difference between the two depending on the mode mixity of the load. So now I go back, I will increase the load again because I'm still below that 1 gigapascal target. So let's go 3 times now because it's almost 1/4. Again, run the simulation, just changing the value of the load. I can, if I have the input file, I can change it directly, that number in the text file, and I can run from command prompt directly as well. So that's also possible in ABAQUS. So now I'm running it. It's taking longer because now it has more deformation into it, but it's still few minutes, less than 30 seconds, I would say. Results, contour plots, and now my stresses are 852, 53 megapascals, right? So I will further go back, increase further. I'm trying to bring it to 1 gigapascals, around 1 gigapascal. So now I change it to 25. It might be slightly higher, but let's see. Still running. Now it's finished. So completed. So now control plots, and so it's now 1.05 or 1.08 or something like that. So I now know my load at which it will fail is around 23, 24. So again, I can fine tune my load and see what values I can be doing. Again, if I have the analytical solution for this beam, I can compare this value directly from there, and that should be very close to that. So again, you can look at any civil structures book and you can find a solution for that in simple terms. Okay, so this was the one case. The second example, I have brought it for a thin steel bracket, same profile, but it's a very thin bracket, and pressure is again 1 megapascals. Material properties are the same. Again, you have to plot the principal stress distribution and compare and find out at which load this is gonna fail. Again, for thin structures, if your load and geometry is symmetric and you have stresses in thickness direction to be 0, which is generally the case in such situations, then you can use plane stress case and you can convert your 3D problem into a 2D problem. So in this case, again, I will still keep it 3D. So what I have to do now, I have the model. I'm not going to repeat everything again. What I will do, I will just go back to my part and I will change the extrude length. So now my thickness is 1 millimeter. So I will change that 150 millimeters or whatever I put to 1 millimeter, and then I will rerun. So you see, you don't need to do everything again and again. You can just use the previous model if nothing, if it's a minor change in the geometry. So here I will just change this to 1. And you see, abracadabra. Now I will just run it again, mesh it again, because now it's a new part, so I need to remesh it. So again, my geometry is not that good, and again in thickness you can see along the thickness direction it's only one element, so it's better to refine it, and that's what I'm trying to do here. Now I will just reduce the approximate element size to 0.25 for this edge. It will delete the element mesh, and then when I press the mesh button, and yes, then it will be something like this. So I have more elements in the thickness. So again, you see, it's not rocket science, it's just your own instincts and the solutions you are trying to make. So I'm just trying to check all the consistencies, so you can do the same. In this case, obviously there are thin elements, and the dimension of the elements in the thickness direction is much smaller than along this profile. So it's giving me highlighted sections. So again, you can go back and modify if you don't like the mesh itself. So I can run it like this and just for demonstration, but what I choose is I just said, okay, let's make it a very fine mesh. So I'm just reducing the overall element size and see what will be the influence of that on this mesh. So it looks much better now, but it's still in the thickness direction. You can see the out of plane thickness direction, or the thickness of the element is much smaller than the other dimensions. So now I'm just trying to go and see what load it's gonna fail. So I will start with 1 megapascal again as a starting point, and then I will run it, submit. and then I can monitor by pressing the monitor button to see if there are any errors or warnings, which are not there right now. There is one warning, as you can see, and you can see the deformation is very high, so its elements have distorted. So now I need to go back and I need to change my model, and you can see my stress distribution is doesn't look very good because it's concentrated in that area, which should be the case, but maybe I need to modify the mesh. So again, mesh sensitivity analysis, that's why I say it's very important, because in many cases you don't have the analytical solution present, so you just try to do mesh sensitivity analysis and see after certain number of elements and geometries, sizes of elements, you will see the results are starting to converge. So I'm trying to change the size now. You see, now I have used a very fine mesh, and again trying to check verifying the mesh to see if there are any errors or warnings. Still I have some elements, a lot of elements with warnings because of this small thickness. So so you can see I'm trying to play around with that now and remeshing it and changing the sizes. Still with this kind of size with 0.5, it's around let's see how many elements it has. So you have like 7,000 elements. It's a very large number of elements, but still it's 2D, so it may survive. But still I will see that you will see that there are highlighted sections, and there are some elements which might have geometric issues. So again, it's your choice, and you can see how it works. Now it's getting better. You see, still it's a small number of elements which have some problems, so you can keep on playing around with this and see what happens. So I'm just going to stick to this one to save time and go back and submit, because it's going to take slightly longer than before, because now we have more than 7,000 between 7 and 8,000 elements. And again I have the problem, so there is some kind of issue with my model. Again, you will come across these kind of things a lot of times. You're doing something and you need to really troubleshoot your model, that what is happening there, so that's what I'm going to do now. I need to do something about my model. So now I'm going to go back, and you can see still I have a lot of load. Although the load is 1 megapascal, my stresses are 56 megapascal or something. Phone me these stresses. So what I do now, I have to find out why this is not converging successfully, why I'm getting the warning message, for example. So have a look at that if you want. So now I'm trying to change the mesh. Most probably it's due to the mesh maybe, so I'm just trying that now. It's a very fine mesh now. I don't think you have to go to that kind of fine mesh, but if you really want to go, you can try it. So yeah, so again I'm trying to see, still small number of elements are giving me some warnings, so you can still play around with that if you want. Otherwise you can live with that, but the element numbers are like now 21,676, which is a very big model. I can also play around with this kind of option and see what it does to my meshing. So when I change this to this, then you will see my element size, it looks much finer, but my element sizes are this. And what I note is, you see I define the edge seeds on this as 3, so it's still using this 3, and maybe these are the elements which are causing problems. So now I'm going to change these edge seeds to the same as the other ones. So that's what I'm trying to do here now. So I will just select the edge, and I will select what to reduce this, how to reduce this. I will select the edge seed, select that edge where we already have 3 elements, press done, and then I will specify, I hope it selects this time, yeah, and then I will reduce it to the normal size or some size smaller than the default. So default is 0.1, but I'm using 0.2 in this case. Let's see what happens. So I remesh this and see how it looks, and ta-da! So it looks very good now, see. And you have to do the same for the other edges, because we defined the seed. So you see, sometimes you take the model from somewhere else and you modify it, but then we didn't pay attention to these kind of things in the main model, so we have to really modify these, and it can take time as compared to before. So again, troubleshooting sometimes can take longer than making the model itself. So that's what I'm doing here. I see it's apply here and then reduce it to the same as the other. So now I'm trying to mesh it and see how it looks. Element size has increased to 61,000. It's a big model now. But even then, if I'm getting some errors, then I need to go back. So now you see at least there are no highlighted regions, so everything seems to be fine, and I am really happy. And I'm going to rerun it, but it will take longer. So let's see what happens. So I run it. So it's still submitted. It's taking pretty long time now, as you can see, because we have huge number of elements. So let's wait for it to go progress. Okay, something is there, so it has finished first increment. So you see, same model was solving in few seconds, 10-15 seconds, and as we refined the mesh to find the best solution, my solution time has increased drastically, computational time has increased drastically. So again, decide on your own what is the best purpose. Again, still it was in within 1 minute time, but sometimes it can go very long. So it's around 81 seconds, as you can see here, CPU time. So more 1.5 minutes or so. And see, now my solution has crashed, because that's why I said I prefer to run it on command prompt, because sometimes if your models are really big and it's CAE is using a lot of resources, then you struggle to open it. So anyways, I have opened the ODB file of the finished analysis, and now I try to see what is happening there. Sometimes you start your ABAQUS, you will see your displays are very small. Again, I have a video on that, but if you really want to see, so for example, you can see the legends of the numbers on this side here are not clear. So what you can do, you can go to the view and you can basically see what is there. So here I'm showing you the maximum principal stresses and the values which you can't read. So you go to the annotation manager and you can just go to any one of those, send for font, select all of these and increase the font size. Say for example, there's a basic quickest way of doing it. So you can see, at least now you can read. So you see the value is now 66.5 or something megapascals. So again, you have to do the same. You have to increase the loads, go back and run the analysis again and again. So hope it makes sense now to do how to perform analysis in 2D. So as I told you, in reality, you can also reduce your 3D problem to 2D problem. And as I gave you an example that for the previous case, for thick bracket, you can use a plane strain case, and for thin brackets, as a thumb rule, you can use plane stress case if loads and geometries are symmetric. So what you will do in this case is, if I want to make it a two plane strain or plane stress case, this is a short demonstration of that. It's not the actual geometry, I just made it just to show you how it looks. So this is a 2D model now, which is 2.5D, which can be plane strain or plane stress depending on thick or thin beam. And here what I have done is I have defined the part as a 2D planar structure, and then in the properties I have defined the material properties as usual, as I did for 3D case with elastic constants. Then I created the sections, and in the sections again I have to select solid, homogeneous, because it's an isotropic homogeneous material, and then assign it to this part. So again, the process is very much the same for 2D analysis. Then I go, and one thing was the thickness of the thing. So if I'm doing plane strain, I have to give the thickness here, or if I'm doing the plane stress, I have to give the thickness in the section part of the properties. So it accounts for that thickness there. Then I stress the part as I did for 3D case. Steps is the same. I created a step, static general step, as I did for 2D case, 3D case, sorry. Once I have done that, then I move to the loads, because there are no interactions here. So I go to the load and I fix on one side here, and I apply pressure of 1 megapascal on this side. I create a mesh. It's much easier in this case because it's a 2D mesh, so you can play around with that. Again, the geometry is very different, no filters, nothing. I'm just created a simple one to save time. And then I select the element type, which could be plane strain, a standard linear in this case, or enhanced hourglass control I have used, and I can run it with the plane stress case, plane strain case. After meshing, I can do the verification as well as I did for the other ones. So again, you can see there are some elemental problem, but again, you can play around with that. I told you in the previous slide or previous video that how you can do that. So again, you can play around with that for mesh controlling the meshing. Then I just go to the job module, create a job and run it. Right, so this is how you will run your plane strain problem, for example. And once you have got the results, you can plot Mises stress or maximum principal stresses and stress, and then see how it goes. Again, if your font size are small in these areas, then you can increase it by setting the font to a very larger value or whatever, or you can do one by one, or you can select all of them. So you will see now the size of all of them will increase. So once you have done that, you can see stresses and you can see compare it with that, and you keep on increasing the load to reach to that. So in reality, they both should give you the same results, whether you're using 2D or appropriate 3D, appropriate 3D and appropriate 2D assumption you have made. So solution should be the same. Now I am trying to do the same for plane stress case or plane stress case. So I will just change this to a smaller thickness, like 1 millimeter in this case, and then rest is very much the same, just the mesh will change because now I have to select plane stress element rather than the plane strain element. So instead of plane strain elements, I'm going to select plane stress element, which are 3PS 4R, which is plane stress elements with 4 nodes with reduced integration. So then I just run it and I get the values out of it. So abracadabra, and then that's it. So you can see it will save a lot of time. The solution computational time will be much shorter, obviously, and you might get this very much the same results with slight differences, because at the end of the day, these are numerical solutions, not the exact solutions. Excuse me. And once this is done, you are ready for comparing with that. So this was just to give you an idea how you can make that. So hopefully this gives you some kind of so hopefully this session would have given you the better understanding of ABAQUS environment, how to construct the models in 2D and 3D. Well, I normally say 2.5D because I prefer to say that if you're using plane strain or plane stress cases. So you learned about the setting up of the model, solving the more static analysis problem, and how to post-process the results. I tried to give you some tips and tricks about meshing. ABAQUS is not an expert mesher, and sometimes people use other meshing softwares like HyperMesh, etc. So you can look into that if you're interested into that, if you have complicated geometries. I also showed you how to convert or assume a 3D problem to a 2D or strictly speaking 2.5D problem. And again, go back to my lectures or quizzes, which I have posted a few weeks back, and that they also give you some information on that. Also, hopefully you will get some basic understanding of what is plane strain and plane stress case. If you still are not clear about any of these things, then please comment or get in touch, and definitely I will try my best to help you out. And that's pretty much it. So thank you very much for watching, and I will come back in near future with a video on the explicit part, or how to perform explicit analysis in ABAQUS. So bye for now and have a great day.